Ankita, let's start.
A very good evening to all the present guests, lecturer and participants. It gives me a great pleasure in welcoming you to this Tech Talk session on CMOS Digital Design, organized by IEEE COMSOC MSIT Student Branch Chapter in association with ECE Department of Meghnad Institute of Technology and Sister Nivedita University. Let me introduce you all with our lecturer and guests. It is a great moment for us to have Emeritus Professor Susanta Sen, Professor in the Department of Electronics and Communication of NIT Durgapur, as our chief guest and lecturer. We are also very delighted to have Dr. Shapnadev Desai, Head of Department of EC MSIT, Dr. Chandipani Ma'am, the Chapter Advisor of IEEE COMSOC MSIT Student Branch Chapter and HOD of EC Department of SNU, and Professor Shantini Sen, Assistant Professor of EC Department of SNU, as our guests of this session. Now I would like to request Dr. Chandipani Ma'am to inaugurate this session and share a few words with us. Ma'am.
Thank you, Ankita. Good evening, respected Professor Susanta Sen, sir, HOD, ECE, Meghnad Institute of Technology, and all my beloved students and participants. On behalf of IEEE COMSOC MSIT SBC, and on my behalf, I welcome all of you to this technical talk organized by IEEE COMSOC MSIT SBC in association with ECE Department MSIT and SNU. IEEE MSIT COMSOC SBC was formed on 2nd June 2016 on the basis of the written approval on 9th May 2016 to provide the opportunity to meet and learn from fellow students as well as faculty members and professionals in the field. Several programs like workshop, seminar, DL talks, industry academia interactions are organized by IEEE COMSOC MSIT SBC throughout the year for the benefit of the student. From these programs, student can get a wide knowledge about the recent technologies and the research domain in technological fields. As a HOD of ECE Department of SNU, I can add that a new advanced electronics lab is going to develop in the department in association with all group colleges. The immediate goal of this lab is to develop a research environment which would support academy and industry both. This lab will have utilization of cutting edge R&D knowledge database in science and in technological areas. In summary, I can say that the key feature of this lab, it should be a state of art lab. It should utilize 24 into 7. It should be self-sustainable by doing industrial project and should have collaboration with some good international universities from the developed countries. For the working of this lab, three main areas are defined for this or identified for this. That is VLSI and circuit, communication and embedded system. Students from all the group colleges can associate with this lab regarding their project work and research activities. Finally, again, I am welcoming all of you to participate the program, listen the lecture, and obviously it will eminently benefit to everyone. Thank you.
Thank you, ma'am, for your valuable words. Now I would like to request the Head of Department of ECE of Meghnad Institute of Technology, Dr. Shapnadev Desai, to enlighten us with a few words.
Good evening, all of you. Respected Professor Susanta Sen sir, Dr. Chondipani Madam, HOD of ECE Department SNU, students, and my dear participants. So good evening all. On behalf of ECE Department of Meghnad Institute of Technology, I, Dr. Shapnadev Desai, HOD of ECE Department, welcome you all to this webinar on CMOS Digital Design, organized by IEEE COMSOC MSIT Student Branch Chapter, Department of ECE of SNU and Meghnad Institute of Technology. Actually, Professor Sen, as I said, was my professor till 2001 in the Department of Radio Physics and Electronics at University College of Science and Technology, which we commonly know as Rajavaja Science College. So he was the professor there. And I'm extremely fortunate. I feel fortunate that I had the chance to listen to his lectures during that tenure. And I would like to inform you all that the ECE department of Meghnad Saha Institute of Technology actually founded IEEE MSIT student branch in 2015. And at the moment, it is having 5 student branch chapters. And 2 of the student branch chapters are actually IEEE COMSOC MSIT student branch chapter and IEEE Electron Device Society MSIT student branch chapter. They were established by the faculty members of ECE department of Meghnad Saha Institute of Technology. As Madam has already said, IEEE COMSOC MSIT student branch chapter was established in 2016. So till then, the chapter has organized many industry academia meets, seminars, workshops, and many other technical talks for the benefit of students. And I am extremely certain that this webinar will be immensely beneficial for all participants today. Professor Sen's words on CMOS digital design actually will be immensely beneficial for me, because personally, if I can say, because I am also in the field of VLSI and microelectronics, and my entire last 12 to 14 years work is based on VLSI and microelectronics. So as I believe that all the participants will actually be immensely benefited from his deliberations today. So once again, I welcome Professor Sen, sir, and all participants to this program. Thank you all.
Thank you, sir, for your valuable words. Now it's time to welcome our chief guest and lecturer of this evening. I would like to introduce and tell a few words about this session's lecturer. Professor Susanta Sen retired as a professor of the Institute of Radio Physics and Electronics, University of Calcutta in December 2016. He is currently an emeritus professor in the Department of Electronics and Communication Engineering, National Institute of Technology, Durgapur, India. He has published around 45 research papers, 6 book chapters, obtained 1 Indian and 3 US patents. During his long career at the University of Calcutta, he served in various administrative positions that include Head of Department of Radio Physics and Electronics and also of the Department of Electronic Science, Dean of the Faculty of Technology and Deputy Director of the Center for Research in Nanoscience and Nanotechnology, CRNN. He has also assumed key positions in the organization of various international conferences. His current research interests are in the area of quantum electron devices, VLSI design, and instrumentation. Professor Sen received the Homi Bhabha Fellowship in the year of 1992. He is a part of the Institute of Engineers India and a life member of the Computer Society of India. Now, I would request Professor Susanta Sen to commence this session. Sir.
Thank you for the nice word of introduction. Let me go to the presentation mode. Is my screen visible?
Yes, sir.
Yes, sir.
Okay. The topic, as has already been announced, choose the display setting, is CMOS digital circuit design. CMOS, the key element in CMOS circuits is a MOS transistor. So let me begin the lecture with a review of the MOS transistor. There's a diagram that shows how the MOS transistor is constructed. We take a silicon substrate. Typically, in this example, I've taken P-type substrate. And in that P-type substrate, 2 regions are doped heavily to N-type, which are marked as N+. This plus, as you know, indicates heavy doping. And the region in between these 2 heavily doped regions is first covered with a thin layer of silicon dioxide, this red layer is a silicon dioxide layer, and on top of that, a polysilicon is deposited, which is again doped N-type, so that it acts as a conductor. Now the name MOS originated from the structure metal oxide semiconductor. In the initial days of the MOS transistor, instead of polysilicon, metal was used as this electrode, and that's why the structure had the generic name metal oxide semiconductor, or MOS. But for technological reasons, since the 1980s, late 1970s and early 1980s, metal as the electrode has been replaced by polysilicon because that provides various technological advantages. But as of today, most of these structures have this type of physical layout where a region is covered with oxide. On top of it, we have an electrode constructed of polysilicon, and the regions on the two sides of that structure, the substrate is doped the opposite type. If you start with a p-type substrate, these regions are doped n-type. If you start with an n-type substrate, these regions are doped p-type, and they are heavily doped. Now they have names. These electrodes have names like source, gate, and drain, and we'll see how these names have originated in course of this lecture. To understand the behavior, instead of taking this three-dimensional view, let's take a two-dimensional view, just the cross-sectional view. So we have the p-type silicon substrate, which have holes as the majority carriers, designated here by this plus signs. The two regions, which we call source and the drain, are doped heavily to n-type. And the region in between the source and the drain, the surface is covered with silicon dioxide. In fact, the silicon is oxidized to create the silicon dioxide. And on top of the silicon dioxide, another electrode, which is a doped polysilicon, is deposited, which is used as the gate electrode. Now, if we don't apply, well, the device actually is a 4-terminal device. The source, gate, and the drain are the 3 terminals that we often use in circuits and depict in the circuit. But the substrate is also a terminal which is always connected to ground for this type of transistor where we have a p-type substrate. Now, so it's a 4-terminal device, but quite often in practical circuit applications, the source is connected to ground. So source and the body are sort of tied together, and that's why the body is not explicitly shown. But let us not consider the source and the drain at the moment. Let's consider just this region from gate through the substrate down to ground through the oxide. As we can see, because the substrate is p-type doped, there is a significant amount of holes here because they are the majority carriers. And if I look into the source and the drain, we have a p-n junction here between the source and the substrate, and a p-n junction here between the drain and the substrate. Now, if you look into these p-n junctions, they're diodes, but they are connected in opposite sense. They're in series, but they're connected in opposite sense. So if I apply an external bias between the source and the drain, then no matter what is the polarity of the bias, one of these p-n junctions would be reverse bias. For example, if we consider the drain to be at a positive potential with respect to the source, then because the substrate is grounded and drain being an n-type region is at a positive potential, this p-n junction is reverse biased. That p-n junction, of course, would be zero biased if the source is connected to ground. But then what happens is, because this p-n junction is reverse biased, current will not flow between the drain and the source. Similarly, if we interchange these two terminals, make this source and that drain, and apply a positive potential on the left-hand side of the structure, then the left-hand side p-n junction would be reverse biased, and again, no current will flow. And here comes the role of the gate. If I apply a positive potential on the gate, then we have an electric field from the gate electrode through the oxide penetrating into the substrate. So this electric field is pointing downwards, and that will apply a force on the positively charged holes downwards. So these holes would be pushed downwards, leaving the region just below the oxide devoid of the free carriers. The free carriers would be pushed down, and this region will be depleted of free carriers. So we have a depletion region where only the ionized impurities which contributed the holes remain. And so we have a negative charge here, a sheet of negative charge here, but that negative charge is a fixed charge because the impurities are bound to the lattice atoms and in the lattice structure, so they cannot move, so they cannot carry current. Only the mobile or free carriers can carry current. So still, when we try to apply a voltage between the source and the drain, the outer electrodes, no current can flow because we have a region which is depleted of charge, that is acting like a dielectric, and so no current can still flow. But if we keep on increasing this positive bias, what will happen is that this depletion region would be pushed downwards, as I've shown here, but because of the increasing field, electrons which were the minority carriers in the substrate will be attracted towards the interface, and also these two regions, these heavily doped regions, will inject electrons into the region just underneath the oxide into the substrate. So it will create a thin layer of mobile electrons, or we can say that the nature of this semiconductor in this region has been converted from p-type to n-type, or in other words, the conduction mechanism has been inverted. That's why we call this thin charge sheet layer of electrons as an inversion layer. So only when we apply a sufficiently large voltage on the gate electrode, this inversion layer is created. And once the inversion layer is created, we see that between the outer two electrodes, we have an N plus structure, and hence on applying a bias, current can freely flow from the drain to the source, I mean the right to the left electrode, or from the left to the right electrode, depending on the polarity of that external bias. Now, if you look at this structure, the structure is perfectly symmetric around the center of it. There is no difference in the construction of the source electrode or the drain electrode. We call one of the electrode source, the other drain, depending on how we externally bias it. For example, if I put a positive potential on this side, that positive potential, positive potential on this side with respect to the other electrode, this positive potential will attract the electrons and drain out the electrons from, it will drain out the electrons from the channel into this reservoir, whereas the drained out electrons would be replenished from the other end, which will push them into the channel. And that's how the current continues to flow. The electrons flow from the source to the drain. So that indicates why we call it the source, because they source the carriers into the channel, and the other electrode drains out the carriers from the channel. That's why they're called source and drain respectively. But since these two regions are exactly identical, if we just reverse the bias, make the left-hand side more positive with respect to the right-hand side, then the current will flow in the opposite direction. The right-hand side will now inject or source the electrons into the channel, and the left-hand reservoir will drain them out. So on that bias condition, the left-hand electrode would be called the drain, the right-hand electrode would be called the source. In fact, we'll see that in course of the operation of the MOS transistor in digital circuits, many times these electrodes reverse their role depending on how the signals change at different nodes of the circuit. Now, all this action, this off condition to on condition, is possible because of this positive potential on the gate, and positive potential in excess of some minimum voltage which we call the threshold voltage, only then this channel is created and we have a current flow. So we can consider this structure, this entire structure, we call it transistor, basically as a switch. With zero potential on the gate, the switch is off, no current can flow between the source and the drain. With a potential in excess of the threshold voltage, the channel is formed and current can flow between the source and the drain, so the switch is closed. And that is why we call it the gate. It sort of opens and closes the path of current flow. That's why it is called the gate. Now, let us look into the operation of the transistor under bias applied to both the gate as well as between the source and the drain. So let's consider this circuit. If we apply a small voltage between the drain and the source, current will flow. We have the channel already by applying a voltage well in excess of the threshold voltage on the gate. And current flows because this channel acts as a simple resistance with ample carrier concentration here to act as a conductor. And so the current linearly increases with the voltage. But as you keep on increasing the voltage and the current increases, there will be a drop across this channel. In fact, there is a drop because the drain end is more positive with respect to the source. And if I consider this channel to be uniform in nature, this voltage drop will be gradual. There will be a continuous drop from this end to that. Or in other words, we say there is a constant electric field from the drain to the source in the channel. And because of this potential drop, what happens, if I look into this formation of the channel, as we discussed in the previous slide, these carriers, the inversion layer carriers, are created by the potential applied on the gate with respect to the substrate. So we need a potential difference between the gate and the substrate to create this channel or have this mobile electrons here. But look at it. The gate is at a positive potential. The source, well, by default, we consider it to be at zero potential. That means it is tied to the substrate. But the drain end is at a much higher potential. If I look into the channel, the drain end is near the drain potential, VDS. So what will happen? If I look into the potential difference across this oxide between the gate and the channel, it is the voltage applied on the gate at the source end. But at the drain end, it is the voltage applied on the gate minus the potential of the drain end, which is VDS. So this potential will be, we can say VGS minus VDS. And because this is smaller, the number of carriers, so the carrier concentration at this end would be less than the carrier concentration on the source end. Pictorially, we can say that the channel would be tapered from the source end to the drain end. As we go closer to the drain end, it will be tapered. And in the extreme condition, when this VGS minus VDS becomes equal to the threshold voltage, the channel will be completely pinched off, as we see in this diagram. Now, under this pinched off condition, the current is going to saturate. Mind you, the current cannot fall, because if the current falls, there will be no big drop across the channel, and it will again revert back to the original condition. But that doesn't happen, because whenever it tries to come back to the original condition, the current will continue to flow. So under this pinch-off condition, the saturation current continues to flow. But beyond this pinch-off condition, the current does not increase anymore. That is to a first-order approximation. But this potential, this voltage, VDS, at which the current starts saturating, would be equal to VGS minus the threshold voltage, which we call VT. Now, what about this saturation current? If you recall the channel formation, the larger the gate voltage, the more would be the carrier concentration in the channel. So higher would be the drain current, the saturation current. So the saturation current will depend on the gate voltage. So if we change the gate voltage and try to draw the characteristics again, we'll get a family of characteristics as shown here. As gate voltage increases, we go to the higher and higher up channels. And in fact, it can be shown that the saturation current is proportional to the square of VGS minus VT. But in general, we can say that the saturation current increases with VG. And we have already discussed that there is a threshold voltage. We need to apply that voltage, that minimum voltage, in order to turn the device on. So, as I said before, the MOS can be used as a switch. Of course, in this region, because the current, the drain current is a function of the gate voltage, we can use it as a transistor to amplify signals, like we use bipolar junction transistors to amplify signals. But today, in this session, we are out to discuss digital circuits. So we will use this property of the MOS transistor, the switching property, because digital circuits are based on switches, and they're also called switching circuits, if you recall. So we'll just concentrate on this switching property. And this is what we use as a circuit symbol for the MOS transistor. Now, we indicate this arrow, we put this arrow to indicate the source or distinguish the source from the drain. And since the gate is insulated from the channel, there's a gap between the gate electrode and the channel. That's the symbol normally used. But as I said, in digital circuits, often the role of the source and the drain can reverse. So we don't use this arrow explicitly. We just use this symbol as the symbol for the MOS transistor. Incidentally, the transistor that we have discussed here, it uses a p-type substrate. So after inversion, the channel becomes n-type, and the carrier of the current carriers are electrons or negatively charged particles. That's why this device is known as an n-channel MOS transistor, or simply NMOS transistor. Alternatively, in the next slide, we'll see if instead of a p-type substrate, we use an n-type substrate, we get what is known as a p-channel MOS device or PMOS device. It is also called an enhancement mode transistor, because what we are doing, we are actually increasing the conductivity of the channel by applying a positive potential on the gate. There is another class of device which are known as depletion mode transistor, where instead of the opposite type of substrate as opposed to the source and the drain, we use the same type of substrate, say N substrate with N plus doping for the source and the drain. And there we apply a negative potential on the gate to deplete the channel, and that's how we control the saturation current again. And that is known as a depletion mode device. Now, depletion mode devices are very rarely used in digital circuits, not for logic circuits. They're used in certain memory array applications only. So we will not spend any more time on the depletion mode device. We'll always be considering this enhancement mode device. And I said that till now our discussions was based on what we call the N-channel MOS transistor, or simply NMOS transistor. As I said, this diagram shows the p-channel MOS, where the substrate, instead of being p-type silicon, is an n-type silicon, and the source and the drain electrodes, instead of being n plus, are doped heavily to p plus. And again, the same thing happens if instead of a positive potential on the gate, we apply a negative potential. Then we first get a depletion, and then the depletion region is pushed downwards, resulting in inversion under the oxide semiconductor interface, and that's how the channel is formed. Now, for this transistor to operate, we need a negative potential on the gate, and again, because we have holes as the charge carriers in the channel, we need a negative potential on the drain to drain the holes out, and source should be at a positive potential with respect to the drain to inject or source the electrode, the holes into the channel. Now, So that's about the basic MOS transistors, the P channel and the N channel. And again, this P channel device is an enhancement mode device. As I said just now, that we'll be concentrating on the enhancement mode device only. So we have the MOS as a switch. And we know from our basic idea of logic circuits that we can use switches to build logic circuits. But before going into that, let's just review our findings. Well, typically we'll be considering what is known as a positive logic system. That means logic 0 is at a lower potential and logic 1 is at a higher potential. And for the purpose of our discussions, we'll take 0 volt as logic 0 and the supply voltage VDD as logic 1. VDD could be 5 volt, 3 volt, 2.5 volt. There are various families of CMOS logic circuits which operate at different supply voltages. So we'll just generically call it VDD. Now for the NMOS, we have seen that if the gate voltage is less than VT, that means when it is logic 0, the transistor is off. And when the gate voltage is at logic 1, that means VG is equal to VDD, the transistor is on. So logic 0 at the gate will turn the NMOS transistor off and a logic 1 will turn it on. But what about PMOS? We'll soon see in order to construct CMOS or complementary MOS circuits, we need both NMOS and PMOS transistors. But if you recall our discussion of the PMOS transistors just a few slides back, you'll note that PMOS transistors requires a negative potential on the gate and negative potential on the drain, keeping the substrate and the source connected to ground. Now that is a big problem when we are using logic circuits or digital circuits. In analog circuits, we have a positive supply and a negative supply. So there it is not a problem. But in logic circuits, we never use a negative supply. Or let's put it this way, we only use a single rail supply, 0 and a positive voltage or 0 and a negative voltage. We don't use 0 as well as both positive and negative voltages. So how to use the PMOS? The point is, if you recall the operation of the PMOS transistor, what it requires is a negative potential on the gate with respect to the substrate. We don't need an absolute negative potential with respect to ground. So there is no hard and fast rule that we'll have to connect the substrate as well as the source to ground, as we have done in case of the NMOS transistor. Instead of that, what we do, we play a trick with the PMOS. We connect the source and the body, that means the substrate, to the supply voltage VDD, which is a positive potential. And if I do that, any potential in our circuit would be negative with respect to the body as well as the source. So any potential here, like a logic 0, will create a negative voltage on the gate with respect to the substrate as well as the source. So with a logic 0 here, this transistor will turn on because my gate to source voltage, the magnitude of the gate to source voltage would be VDD. Of course, with gate negative with respect to the source and substrate. And that is a condition under which the PMOS transistor will turn on, the inversion layer will form. Whereas, if we apply a logic 1, the voltage being VDD, the gate to source and gate to substrate voltage would be 0. And so the PMOS transistor will not turn on. So from the operation point of view, we find that it works the other way. The NMOS turns on with a logic 1, whereas the PMOS turns on with a logic 0. Now, conventionally, we are used to thinking 1 as an on state and 0 as the off state. And to be commensurate with that, we have introduced, or the scientists have introduced, a circle here. In digital logic terminology, it's called a bubble that indicates an inversion. So if it indicates that if I apply a 0 here, it will turn on. So the symbol of the NMOS transistor is modified with a bubble in the gate to create the symbol for the PMOS transistor. So as I have just said, that with VG must be greater than or equal to VDD minus VT to turn it off. And with logic 1 being VDD, it's definitely greater than VDD minus the magnitude of the threshold voltage. I say magnitude because the threshold voltage for the PMOS transistor is a negative quantity. And with a logic 0, it is on. Okay, so that's the way we use these two transistors. But there is a catch when we use transistors as switches. If you recall the construction of the transistor, there's a PN junction here between the drain and the body. There's an oxide between the gate and the body. So all these things forms capacitors. The junction between the gate and the body, the PN junction, have a capacitance of the depletion layer. The oxide being separated by the channel and the gate electrode, it forms a parallel plate capacitor, and that produces a capacitance. And these are capacitances that come into the device and as a result into the circuit as a result of the construction of the devices. We do not explicitly connect in capacitances, but these capacitances are there. There's three capacitances, or parasitic capacitances as they are often called. Now the presence of this parasitic capacitance have a bearing on the operation of the transistor as a switch. Let us consider an NMOS switch. And let us initially consider that this capacitance on the right-hand side of this switch is at zero potential. That means there is no charge on the capacitor. We have applied a logic 1 at the other end. That means the other electrode of the transistor. And let us say at time t equal to 0, we have, well, the gate was initially at logic 0. So the transistor was off, so no current was flowing, and the capacitor was at zero potential. But at time t equal to 0, we apply a logic 1, that means a voltage VDD on the gate to turn this transistor on. Now, as we discussed, when we discussed the operation or the physics of the transistor, the channel forms a resistance. So between the drain and the source, in this condition, the left-hand side is the drain, as you can see, because the left-hand side is at a positive potential. The right-hand side electrode is at zero potential because there is no charge in the capacitor. So this is acting as a drain, that is acting as the source. So the current will start flowing from the drain to the source through the channel, but the channel has a finite resistance. So this potential here will not immediately change from 0 to 1. Rather, it will charge with the time constant R into C exponentially, and it will go up like that. But the point is, as the potential increases, the source potential, initially it was 0, but the source potential keeps on increasing. The drain potential is at VDD. Initially, because it is at VDD, the gate is at VDD, the transistor is in saturation. The source potential was 0, so we had the maximum channel capacity. So the saturation current was flowing, but the saturation current will keep on decreasing because the source potential is increasing, and hence the gate to channel potential or the gate to source potential is decreasing. But as the source potential approaches VDD, a point will be reached which will be where the potential in the capacitors, that means the potential of the source, is below VDD by this amount VT, the threshold voltage. When that happens, the channel is cut off. Mind you, this is not pinch off. Pinch off happened because of the current flow. But now, because the gate to source potential have come down to less than VT or equal to VT or just less than that, the channel ceases to exist. And if the channel does not exist, there can be no more current flow. So under this condition, the capacitor or the output potential, if I consider this side as the output of the switch, the potential at the output of the switch will exponentially reach VDD minus VT. It will never reach VDD. Well, that is still not a problem from digital logic point of view, because typically we consider VDD by 2 as the logic threshold. Any voltage below that is considered as logic 0. Any voltage above that is considered as logic 1. And VDD minus VT can always be designed to be well above VDD by 2. So it still can be considered as logic 1. Yes, it is logic 1. But there's a catch. We'll discuss that. But before that, let us see what happens if we try to transfer a logic 0 using the NMOS switch. Let us consider, well, that's a thing I have already discussed. Now, it's called the weak 1 for a reason I'll discuss in the next slide. But before that, as I said, let's consider the other operation. Now, for this purpose, let's assume that due to some previous operation, the capacitor has been charged to VDD or near VDD. And that we have applied a logic 0 at the left end. And again, as before, at time t equal to 0, we turn the switch on by applying a logic 1 on the gate. Now look at it. Under this bias condition, the right-hand electrode will act as a drain because this is at a higher potential at VDD, whereas the left-hand electrode by the external input is now at 0 potential. So this will act as a drain, that will act as a source. And when the transistor turns on, current will flow in the opposite direction. That's why I said that in digital logic, the source and the drain often changes their respective operations or respective scenarios. So that's why we don't explicitly put an arrow to indicate that this is the source, as we do in analog circuits. But let us continue with the discussion. Again, if I turn the transistor on at time t equal to 0, the capacitor will start discharging through the transistor down to ground because we have connected a 0 volt here. Now look at it. If I consider the channel is pinched off at the right end. In the earlier case, the channel was pinched off at the left end, and the channel was getting constricted on the source end as the capacitor was charging. In this case, the channel is formed between the source, which is at 0 potential, and it is constricted at the right end due to pinch off because we have a potential VDD here. But as current flows, this potential will drop because the capacitor will be discharging. And as it drops, it will gradually come out of the pinch off condition and the channel will start widening here. And the transistor will come out of the saturation region and enter into the linear region of the characteristics, if you recall the IV characteristics of the transistor. As far as the source potential is concerned, it is firmly held at 0 volt by the input signal. So the gate to source potential is always equal to VDD. So the channel is always formed. It never sort of cuts off. And the transistor also comes out of the pinch off condition and gradually the channel is wide open. So there is no impediment to discharging this capacitor down to 0, as we had in the case of the charging condition. It would charge only up to VDD minus VT, but during discharging, it will come down to 0 potential because the transistor is fully on. And that's why we call this as a strong 0, because we have a low impedance between the output and the input, whereas in this case, there's a high impedance between the output and the input. We'll see what is the role of this low and high impedance shortly, and that we can understand from this equivalent circuit. Let's consider a general case. We have some input signal, Vi. We have a capacitor. And again, we have turned the switch on by applying a voltage VDD. Now, obviously, when we turn the switch on, this capacitor will assume the potential Vi. If Vi is less than VDD, it will be Vi. If Vi is equal to VDD or greater than that, it will charge only up to VDD minus VT, as we have discussed before. But let's consider the general case. In general, although this is the circuit that we have actually wired up, and the capacitor, of course, came from parasitic components, but they are from the devices that we have used in the circuit. But we cannot isolate this circuit from the environment. In our environment, there is a lot of electromagnetic signals. Well, nowadays, the amount of electromagnetic signals in the environment is very large because of the large-scale use of mobile communication devices. But even without that, even if we don't have mobile phones in the neighborhood, we have the power lines which carry 50 hertz electrical signals. And any conductor through which the current varies with time gives rise to electromagnetic radiation. That's a property of electromagnetism. So our environment is full of electromagnetic signals because there's power line conductors act as radiating antennas. And also, a law of physics is that a good radiator is also a good receptor. Now, when we construct these circuits, we use electrical conductors or wires or strips of copper to make these connections. And these conductors will act as receiving antenna. So when put into the environment of this electromagnetic signal that is there in the atmosphere surrounding us, these conductors will sort of pick them up and produce voltages across them. And these are what we call noise because they're unwanted signals. We don't want it, but they creep in. They come from the surroundings, from the disturbances or electromagnetic disturbances, as I should say, in the neighborhood. So we can say that the circuit is not just this much. There is some source, which we call the noise source, which is sort of injecting a noise signal onto this node. And this result of the noisy environment and the conductor acting as a receiving antenna can be sort of equivalently represented as a noise voltage Vn with a source resistance Rn. Now, if I look into this node, now there are two competing signals which is trying to modulate the voltage here. One is what we want, our input signal Vi. The other is this unwanted noise. And let us see what is the result. If I work out the potential here, we can simply use what is known as superposition theorem in circuit theory to find out what will be the voltage. What superposition theorem says is that in order to find out a node voltage in presence of multiple sources, all you do, consider all voltage sources except one as short circuit and all current sources as open circuit. So if I try to find out the voltage due to one of the sources, say Vi, in this case, we'll consider Vn to be short circuit and leave the resistance as it is. So only the voltage source should be replaced by its equivalent resistance. The ideal part of the voltage source should be short circuited and try to find out what is the voltage here. And similarly, we'll short circuit the other source and consider the voltage here due to the noise. And if there are more than that, there are many other sources, we'll do it similarly for all of them, considering one at a time. Now, in our case, we have only two. So when we do this, and then all we have to do is to add up the voltages due to the individual sources, and that will give the net voltage here. So by superposition theorem, we can say that this voltage would be Vi times Rn upon Rds plus Rn. That is when Vn is short circuited. And well, Rds is the drain to source resistance of the MOS transistor, of course. And Vn times Rds upon Rds plus Rn when we take Vi short circuited. And we have summed them up. So the voltage on the capacitor is given by this. Now here comes the catch. There are two conditions. When Vi is VDD, well, the gate voltage is always VDD to turn the transistor on. When Vi is VDD, the gate to source voltage is less than Vt. And so Rds must be replaced by the off resistance of the transistor. Well, even when we turn the transistor off by applying zero voltage between the gate and the source, still a current flows between the drain and the source because a reverse biased PN junction is not totally off. the reverse saturation current flows. So that sub-threshold current flows, but that's a very, very small quantity, and hence the effective resistance is very large. And we may say that R off is much, much greater than Rn, the noise source resistance, which is typically of the order of a few hundred ohms. Whereas R off is of the order of megaohms, or maybe even more. So when we apply that here, we just rewrite this expression into this form by sort of dividing the numerator and denominator by R off. And here, because R off is much larger than R on, this can be sort of neglected. The denominator is 1. And here also, this factor can be neglected. So the net result is Vn, or in other words, the potential here would be dominated by the noise source, not the input signal. So if you recall, when we are trying to transfer a logic 1, that means put Vi equal to VDD, I said the transistor turned off at the end of the process, resulting in a weak signal at the output. Yes, it did charge to a logic 1, but that condition can be disturbed by the noise very easily, because noise would be dominating. That's why we say that the logic 1 that we got at the output of the switch is a weak one. Whereas when Vi is 0 volt, VGS is always equal to VDD, and RDS is R on, which is like a few ohms only, which is much, much less than the noise source resistance, which, as I said, few hundred ohms. So again, we use a similar analysis. Instead of dividing throughout by R off, we divide by R on, Rn. And then we have this condition where, because of this condition, this term can be neglected, the denominator is 1, and the noise component can also be neglected. And so the output would be equal to input. So the input is controlled by the signal. Noise have very little effect. Noise cannot affect it. So we say that the signal is on firm ground, and we say it is very strong. So that's why a logic 0 transferred by the NMOS switch is considered a strong 0, whereas a logic 1 transferred by the NMOS switch is considered a weak 1. In case of PMOS, just the opposite will happen, because in order to turn the PMOS on, you have to apply a 0 volt or a logic 0 on the gate. And so when a logic 1 is transferred, at the end of the process, the source and the drain both are at logic 1 or VDD. The gate is at 0 potential. So the gate to channel potential is minus VDD. And that high negative potential is required to keep the PMOS on. So we have the on resistance and we have a strong 1. But when you try to transfer a logic 0, we get a weak 0 for the same reason, because at the end of the process, the gate is at 0 potential always to turn it on. But at the end of the process, the drain and the source, all of them come to 0 or near 0. And that's why it discharges down to VT, the transistor turns off at the end of the process, and the output again can be dominated by noise. So we say it's a weak 0. So that is where the requirement of PMOS and NMOS switches are arise in the design of logic circuits, because we don't want a weak signal at my output of any logic gate. We always want a strong signal, whether it's a 0 or 1. But as we have just found out, only PMOS can provide a strong 1, and only NMOS can provide a strong 0. So we need to use both of them in order to construct a really good logic circuit. And that's how the CMOS philosophy has emerged. Now, before going into the details of the CMOS logic circuit, let me just revisit switching theory using switches. If we have two switches, physical, electromechanical, or simple mechanical switches in series, then we find that if both the switches are on, then the output F would be equal to the input C. this symbol IEFF stands for if and only if. It means that this condition is defined only under this condition A and B being true. That means both A and B being on. If this is not true, we do not know what is the outcome of F, because if one of these switches or both are off, there is no connection between the input and output. But when the switches are in parallel, we see that it sort of simulates the OR operation in Boolean logic, because OR means if either one of them or both of them are on, the circuit is on, and so output would be equal to C. So if equal to C, if and only if A or B is 1 in the parallel connection, and output equal to C if and only if A and B is 1 in the series connection. Now let us try to work it out with our transistor switches. Let us start with the NMOS switch first. Now, as you've seen, we want a strong output. So there's a constraint. When we use NMOS switch, the input side must be 0. So with input side 0, we see that F would be equal to 0 when A and B is true. Now when A and B is true, but the output is 0, that is, by the definition of Boolean logic, it is known as the NAND operation, not AND. So it mimics the A NAND B operation. Let's look into the truth table. Both A and B are 1, the output is 0. But what happens under other conditions? Well, we cannot say that, because if any of these inputs, A or B, or both are 0, the circuit is off, output is floating. And we have seen that in practical transistors, there are this parasitic capacitance, and whatever charge the capacitor had held due to some previous operation will prevail here when we turn the circuit off. So we cannot predict for good what is going to happen to F when under any of the other 3 conditions. But nonetheless, we'll take care of it later. For the time being, let's see what happens when we have the transistors in parallel. So we have a parallel connection here. And if we have a parallel connection, again, F would be equal to 0 when A or B is true. And that is, by definition, is the NOR operation. Again, if we look into the truth table, A or B is true means any one of them or both of them are 1. Under those conditions, in each of these conditions, the output is 0. But when both the switches are off, again, we do not know what is going to happen to the output. But these question marks are answered by the PMOS switch, because from our knowledge of logic gates, the NAND gate and the NOR gate, we know that under these conditions, the output would be 1. And a logic 1 is transferred by PMOS networks. So look at the parallel connection of the PMOS network. Now, in order to turn the PMOS on, as we have discussed many a times by now, we have to apply a logic 0. So A must be 0 or B must be 0 to respectively turn this transistor or that transistor on. So when A is 0, we say that A bar is 1. And when A bar or B bar is true, that means either this transistor is on or that transistor is on, or both of them are on, the circuit is through. There's a connection between left hand and right hand. And because the left hand, by the constraint that C must be equal to 1, the input must be equal to 1 for PMOS, the output assumes 1. Now, A bar or B bar, by De Morgan's law, is A NAND B. So that fills the gap of the first 3 rows of the truth table of the NAND gate. 0, 0, 0, 1, 1, 0. In all these conditions, the output is 1. So my truth table, these 3 conditions are fulfilled. The last condition had already been fulfilled by the series combination of the NMOS transistors. If I look into the series combination of PMOS, again, by the same logic, when both these transistors are on, F is equal to 1. And again, to turn this on, A bar must be 1. To turn this on, B bar must be 1. So A bar and B bar must be true in order to get a 1 at the output. And again, by De Morgan's law, A bar and B bar is A and B. So that takes care of the first row of, A nor B, the first row of the NOR gate. So we see that for an effective logic circuit, for creating an effective logic circuit, we need a pull-up network which connects the output to VDD or makes the output logic 1 when the function is supposed to be true. And for the technological reasons that we have discussed today, this pull-up network must be built using only PMOS transistors, because then only a logic 1 can be strongly transferred to the output. And at the same time, we need a pull-down network which will connect the output to ground when the function is supposed to be false. And again, for the technological reasons, again, this pull-down network must be built using only NMOS transistors. So a complete working logic circuit must have a pull-up network and a pull-down network. The input must, of course, be connected to both of them. The input set that makes the output 1 will turn on the pull-up network, and the input set that makes the output 0 will turn on the pull-down network. Only pull-up or pull-down, not both of them at the same time. And that is because if I look into a set of inputs and plot them on a Venn diagram, say the points here are the different sets of inputs, and for each combination or different combinations of input, I should not say sets, the different combinations of inputs, each combination is a point in this world space. And there is a subset of points for which the output is 1. There is another subset of points for which the output is 0. And mind you, there cannot be any overlap between this 0 subset and the 1 subset, because a logic circuit output cannot be both 1 and 0 at the same time. It has to be either 1 or 0. So these two subsets are clearly demarcated, and these two subsets together form the complete set, or the universal set as it is known in set theory. And when that happens, the two subsets are referred to be called complement of each other, and they're called complementary subsets. And if I look into the circuits, the pull-up network and the pull-down network performs complementary tasks. One makes sure that this subset is satisfied, the pull-down, and the pull-up network satisfies that the complementary subset is satisfied. That's why we say that the pull-up and the pull-down network are operationally complement of each other. And as a result, the logic circuit is known as complementary MOS logic or CMOS logic. Well, operationally, they are complement of each other, but we have seen that in order to achieve these complementary functions, if the PMOS transistors are in series, the corresponding complementary part of the logic must be performed by a parallel combination of NMOS transistors and vice versa. So we say that they're topologically dual of each other. A parallel circuit and a series circuit are known as dual of each other. So we say topologically they are dual of each other. Now, these are some of the simple gates. We have already discussed the NOR gate and the NAND gate. We have seen that the one subset of the NAND gate is performed by a parallel of two PMOS transistors, and the 0 subset of the NAND gate is performed by the series combination of NMOS transistors. So we combine them to form the NAND gate, and we see that for different input combinations, you can verify it by considering A and B or combinations of A and B as 0, 0, 0, 1, 1, 0, 1, 1, and so on. And you'll see that under some conditions, the upper half of the circuit would be on while the lower half would be off, keeping F equal to 1. That means F would be connected to VDD. And for the other sets of inputs, the lower half would be on, the upper half would be off, so F would be 0. And similarly here. Now these are some of the basic gates, but let us try to understand how general purpose CMOS logic can be designed. Let us consider a typical function. Say F equal to the complement of A and B or C. Now, there's a simplicity in the design of CMOS logic. As we have seen, as we have observed, that the pull-up and the pull-down networks are topologically dual of each other. We don't need to individually design each of the networks. We just design one of the networks and simply by observation draw the dual network for the other half. So we'll start this design by working out the pull-down network first. Now what the pull-down network is supposed to do? It is supposed to, pull-down network will connect the output to ground when F is false. That means this function is 0. Okay. Now F is false means F bar is true. That means A and B or C is true. Now this is the condition when the output should be connected to ground. So first of all, we have to design a network of switches by which will turn on and that will connect the output to ground. So one end of that network should be connected to ground, the other end should be connected to output. So when that network is on, that means there's a connection between the two ends of the network, output would be 0. Now we see it's A and a combination. Let's call it X for the time being. So A and X means the two switches, which one will operate with A, the other will operate with X. They should be in series. So we start with A, an NMOS transistor, because we are designing the pull-down network, so we have to use NMOS. And in series with that, we need something that will implement X. Now X is B or C, and OR function is implemented with two switches in parallel. So we can connect two NMOS switches in parallel. And that parallel combination is connected in series with the transistor A. So this is the network. Now when A is on, that means A is 1, this transistor is on. When either B or C is 1, this combination is on. So we have an end-to-end connection. And so when A is 1 and B or C is 1, this is true. So the output will become false. That's what we need. F bar should be 1. That means F should be 0. So we connect one end to ground, and obviously the other end is the output of the network. But this is only the pull-down network. As I said, to get the pull-up network, all we have to do is to draw the topological dual. Let us see how to go about it. We see that in this network, we have a transistor A, which is in series with a combination. So in the dual network, A should be in parallel with that combination. And what is that combination? In this network, they are in parallel. So that combination in the dual network must be in series. So we have that A in parallel with the combination of B and C. And because B and C were in parallel in the pull down, they are in series in the pull up. So that is the complete network. And again, you can verify that this actually implements the logic function F by considering the different combinations of A, B, and C. Identify these transistors as Q1, Q2, Q3, Q4, Q5, and Q6, and find out which of the transistors are on and which are off under the different input conditions, and find out whether F is connected to VDD or ground. That's how you can complete the truth table and indeed verify that it implements this function. So this is the way to design CMOS logic. I think I have used up my time, so we'll stop here and leave the floor for discussion.
Thank you, sir, for sharing your in-depth knowledge and expertise with all of us, and I'm sure all the participants have gained immense knowledge as well, which will prove to be of great value in their journey of understanding the vast and fascinating field of electronics. Now we shall start the Q&A session, and feel free to ask questions to Professor Sen on this session's topic.
Stop sharing and to leave the floor open.
Ankita, there is a question in the chat box.
Yes, ma'am. The participant is asking what is the use of CMOS in FPV cameras of UAV?
Sorry, can you, well, is it in the chat box? Let me look in the chat box. Well, I did not have the time to discuss the details, but if you look back into our discussions today, in the CMOS circuit, under the steady state condition, that means when the output is steady at either logic 0 or logic 1, only one of the two halves is conducting. So there is no current flow through the network from supply to ground. Well, by no current flow, I again say that only the leakage current flows, but that's negligible as compared to the normal operating current of transistors. So CMOS is by default, they consume very little power. The power dissipation is very, very small compared to logic circuits using bipolar transistors or simply NMOS or simply PMOS transistors, where a significant amount of current flows from the supply to ground even under steady state. Here, current is actually drawn from the supply only when the output is switching. That means changing from 0 to 1 or 1 to 0, because during that condition, the capacitor will charge up or discharge, and this charging will require a current to be drawn from the supply through the pull-up network. So power is dissipated in the resistance of the pull-up network, and when the capacitor is discharging, it is again sending current through the pull-down network, so energy is dissipated in the resistances of the pull-down network. So only during switching, significant amount of power dissipation takes place. So we call it dynamic dissipation, as opposed to static dissipation, which is a much larger amount in case of bipolar logic. So CMOS is by design a low power device or a low power circuit. Now in unmanned aerial vehicles or in any mobile applications for that matter, everything depends on the battery life, and we want to extend the battery life as much as possible. Now we can have extended battery life by two ways. One, by increasing the capacity of the battery, but that will increase the weight, and hence there will be energy dissipation elsewhere. Like in order to put the vehicle airborne, we need to spend a lot of energy, and that energy also have to come from the battery. Or otherwise, we just reduce the energy dissipation, and for that, CMOS is the most appropriate technology. And that is why almost 99% of digital logic today are designed using CMOS circuits. Any other question? Well, as I said, CMOS, what I have discussed today is the method of general purpose logic circuit design for image sensing or image processing or any other application like communication, speech processing. We need different kinds of digital logic circuits. All you have to do, you need to know what kind of a logic function, a Boolean function, you need to implement that application, to sort of fulfill that application, and then design a CMOS logic to implement that Boolean function. That's it. That's a good question. The point is, what's happening in industry, particularly integrated circuit industry, the second advantage of MOS technology, and hence CMOS as well, is that the fabrication technology is much simpler compared to that of bipolar transistors. And as a result, it was possible to reduce the size of the transistors. Now, I was talking about the stray capacitances or the parasitic capacitances. The parasitic capacitances obviously depend on the dimensions. The larger the area, larger is the capacitance. And larger the capacitance, slower it is, number one. And number two, it will require more charge to charge up and charge down. And more charge transfer means more energy dissipation. So if you can reduce the size of the transistors, you reduce the size of the capacitances, and hence both improve speed as well as reduce power dissipation. And that's why industry since the 1980s had been aggressively scaling down the size of these devices. In fact, when CMOS first came into the market in the late 70s or mid 70s, the size of the transistors were like, the typical drain to source distance was like 10 micrometer. Now it is less than 10 nanometer. In fact, just about a month back, there was a news item in Times of India that Apple in their latest generation mobile phones is using 5 nanometer technology transistors. That means the source to drain distance is only 5 nanometers, the minimum feature size that is called. So with 5 nanometer, as opposed to 10 micrometer, you see, there is a 10,000-fold reduction in each of the dimension. Means there is a 10 to the power 8 times reduction in the effective areas. Or in other words, there is a corresponding reduction in the capacitances, and hence reduction in the time delay or improvement in speed, and reduction in energy dissipation per gate. But mind you, per gate, I said, what happens with this reduction in the size is that people are trying to put in more and more transistors to build more and more complex circuits, and hence get more feature-rich mobile phones and tablets and other handheld devices. And hence, the circuit size is increasing. Although per gate energy dissipation is reducing by that large factor, the overall energy dissipation is not really going down that much. It is still a significant amount, and that's why the batteries of our mobile phone usually drain in a few hours for many people. For me, probably it lasts for a day because I don't use mobile phones that much. But the younger generation is always on it, and they lose the battery charge within a few hours. Now, here comes the point, why high-K dielectric is used. Now, as you reduce the dimensions, you're reducing every dimension. Not only the length of the transistor, but the thickness of the oxide, the size of the source and drain electrodes, the size of the gate, and everything. Now, it is the thickness of the oxide that becomes an impediment, because as you reduce the thickness, there's a possibility at some point that when you apply a gate voltage with respect to the channel, the oxide no longer acts as a dielectric. There's a phenomena called quantum mechanical tunneling, by which electrons can transfer between the channel and the gate, or vice versa, depending on the polarity of the bias. And in order to reduce this tunneling or keep it insignificant, you need a minimum thickness of the oxide. But the problem is, if you increase the oxide thickness, the effective capacitance decreases. And if the effective capacitance decreases, what happens is that you need a larger voltage on the gate. Now, but larger voltage on the gate means larger voltage on the source and the drain. And that brings in other effects, like there can be sort of avalanche multiplication in the channel. There are other factors which are known as hot electron effects. So as we reduce the size of the transistor, we reduce the supply voltage as well. At the beginning of this lecture, I said that VDD could be 5 volt or 3 volt, 2.5 volt. In the most recent set of devices, VDD is less than a volt. It's like 0.7 volt. Now, when you have such a small voltage as logic 1, and if you have a thick dielectric, you would be able to create the inversion layer in the channel. That means channel will not be formed. And as a result, the transistor will not work. Now, if we, instead of silicon dioxide, we use a dielectric which has a high dielectric constant, then even with a thicker dielectric, that means the oxide thickness being higher, because of the high dielectric constant, we can have the same capacitance as a thin silicon dioxide layer. So that's where high K dielectrics come in. Okay, what is the limiting condition that prevents us from further scaling down at the nanometer level? As of now, it is still the technological limitations. People are trying to find out methods of scaling down. And as I said, just about a month back, there was this news item that commercial 5 nanometer devices have been used in chips. Well, discrete devices, even 4 nanometer has been demonstrated in the laboratory scale, but they're not yet commercially used. There's, of course, a physical limitation. You cannot go beyond less than 1 atom. But the atomic distance in silicon crystal lattice is of the order of 2 of the order of 1 point something nanometer. I don't have the exact figure. I'll have to check. Without a silicon atom, of course, a transistor cannot work. Okay, the classical CMOS device or the MOS device is what we have discussed today. In this small geometry, this planar structure is not there. It's rather the channel is like a wire, a cylindrical rod, and the gate is a cylindrical shell surrounding the channel. These are known as gate all-around structures and often called nanowire MOS. Any other question?
I think that is all the questions we have for now. Thank you to all the participants for asking such well-thought questions, and thank you, sir, for answering them. I hope everyone has filled up the feedback form to get that will.
Ankita, just before ending the session,
Yes, ma'am.
just one thing, that is, please switch on all the videos of the participants so that
Yes,
we can
ma'am.
take a snap.
Yes, ma'am.
Take a snap. Yes.
Yes, I request all the participants to turn on their video. We'd like to capture a group picture. Okay, thank you. It's been taken. Thank you, everyone.
Okay.
Ma'am, thank you.
Now I would like to request Professor Shantini Sen ma'am to give a vote of thanks.
Nivedita, on behalf of the IEEE Communication Society, Student Branch Chapter at the Meghnad Institute of Technology, and the Electronics and Communication Engineering Departments of both Sister Nivedita University as well as Meghnad Institute of Technology, it is my great pleasure to thank our speaker, Professor Susanta Sen, for his enriching talk on CMOS Digital Design today. Thank you, sir, for taking the time. We also thank Professor Dhrubajyoti Chattopadhyay, the Vice Chancellor of Sister Nivedita University, Mr. Shumon Chatterjee, Registrar of Sister Nivedita University, and Dr. Shonku Bose, the Chief Executive Officer of Techno India Group, for their encouragement and support at every step. This event would not have been possible without the active participation of the students of the Electronics and Communication Engineering departments of both Meghnad Institute of Technology as well as Sister Nivedita University, and the guidance of Dr. Chondi Pani, who is the head of the Electronics and Communication Engineering Department and SNU, and also the Student Branch Chapter at MSIT. We also thank Dr. Shopnodip De, the head of the department of the ECE Department at Meghnad Institute of Technology, for all his help. The cooperation and support of the staff of both SNU and MSIT was also extremely helpful. Finally, a special thank you to everyone who joined us today for this talk. Between Google Meet and Facebook Live, there were more than 100 participants, and we thank you for making this program a success.
Thank you, ma'am. This brings us to the end of the session. Thank you, everyone, for attending this session. Thank you.
Okay.
Thank you. Thank you, sir, for the wonderful talk. Thank you so much.
Thank you very much, sir.
Thank you so much, sir, for this wonderful session.
Okay, so let us call it a day. Just logging out.
Yes, sir.